All right, so we've made some really good progress toward having a version of proof of stake random sampling that has the additional secrecy property that we want. That it's only the owner of the public key that gets sampled who finds out that they got sampled. On the other hand, if they want to convince everybody else they got sampled, that's easy to do as well. And so the big ingredient that we're using in this current approach is a verifiable random function, or VRF. So remember, given a VRF, our approach to sampling a public key, each owner of each public key evaluates the VRF using their own private key, and then we define that public key as being sampled if and only if the VRF output, again with the corresponding private key, is sufficiently close to 0. Okay, so note that each owner of each public key is going to be getting a different VRF output because each owner of each public key is using a different private key when they evaluate the VRF. The defining properties of a VRF then give us the properties we wanted of a proof of stake sampling scheme, right? So first of all, we wanted it that the owner of a public key should be able to just check whether or not it has been sampled. And it can do that because property 1 of a VRF is that it's easy to evaluate if you know the appropriate private key. Secondly, we wanted to make sure that, if someone sampled, they can convince the rest of the world of that fact. And so that follows from property 2 of VRFs, which is if someone knows your public key and you tell them the alleged VRF output with your private key, then they can easily check that that is in fact the case. So you can check if you got sampled. If you did get sampled, you can tell everyone else about that in a verifiable way. The third defining property of a VRF is what gives us the secrecy property that we wanted, right? We want it to be the case that nobody could tell if you've been sampled, if you're the leader, unless you tell them so. And that's exactly what the third property says. It says someone who does not know the private key and also is not told the output of the VRF cannot themselves figure out what the output of that VRF is. So they can't figure out whether you've been sampled or not. And finally, in order to get the details right around what sufficiently small means, we're going to want the output of VRFs to be, for all practical purposes, indistinguishable from uniformly at random. So in particular, if you're feeding in random inputs, like the output of a randomness beacon, to a VRF, the outputs you're going to see are going to be basically as good as uniformly at random. We also talked in the last video about a canonical construction of a VRF, which is really just to use a digital signature scheme, with signatures kind of playing the role of VRF outputs. You do want to use a signature scheme that has unique signatures. So for a fixed message and a fixed secret key, there's only a single signature, which would cause anybody who knowing the public key to accept the signature. Right, if you don't have that property, then you can grind over multiple possibly correct signatures, which would manipulate the randomness. You don't want that. So you really want unique signatures. If you feel like the signatures you're getting from your signature scheme are basically uniformly random already, then you're done. If not, then you should feel free to pass those signatures through a cryptographic hash function for which you're comfortable making the random oracle assumption. So that summarizes the really healthy progress we made in the last video, but we are not done. Right? We already mentioned sort of issues 1, 2, and 3 in the last video. That's what led us to the definition of a VRF, but there's 2 more things we have to discuss. One is a major complication that arises in proof of stake sampling using this VRF approach, and so we need to talk about what that is and what we can do about it. And then I also want to spend some time filling in the details of how to define sufficiently small in a way that gives you Sybil resistance. So issue number 4 is actually a pretty major complication of using this VRF approach to do proof of stake sampling. And I'll bet a bunch of you have already kind of noticed this issue. To get the secrecy property that we're after, right, we're having each of the public key owners independently evaluate the VRF. So each owner of a public key might or might not be selected with some probability, but they're basically like independent coin flips. Which means there's a chance that, first of all, nobody gets sampled, right? Maybe all of the owners of the public keys evaluate their VRFs. None of those VRF outputs are sufficiently small. Similarly, it's possible that 2 or more of those VRF outputs qualify as sufficiently small. So when we're talking about sort of sampling from the list of public keys, obviously we always had in mind, like you sample 1 and exactly 1 public key out of PK1 through PKN. That is not actually what we're getting out of this VRF approach. We're getting a variable number of samples from the list. Now we can tune that difficulty parameter tau so that we expect to get, say, exactly 1 public key sampled, but there's going to be variance around that, right? Because these are basically independent coin flips. We might get 0, we might get more than 1. We can also fiddle with a difficulty threshold tau to trade off between those two bad cases, right? So if we tune tau so that we expect to get, I don't know, like 5 samples at a given time step, well, then it's very unlikely we're going to have 0, but of course it's very likely we'll have 2 or more. Alternatively, if we tuned the parameter tau so that we were expecting to get in an average time step 1/10 of a sample, well, now all of a sudden it becomes not impossible, but unlikely that we'll get 2 or more. On the other hand, a lot of the time we won't get any. So you can kind of trade off these two bad cases of having no samples or having multiple samples, but you can't really get rid of either of them. So that's actually a major issue. So let's talk through sort of 3 options you have for dealing with it. So option number 1 is just to punt, frankly. You could say, you know what? In the abstract, this sort of secrecy property seemed like something that would be nice to have. But now that I see the costs that I would have to pay using this VRF approach, where I might have to deal with like 7 different public keys sampled like in the same round, like what do I do with that? You could say, yeah, you know what? It would have been nice to have, but it's just not worth having to deal with. So let's just give up on secrecy. So what this means is getting comfortable with the fact that everybody's going to find out who the leader is at exactly the same time. And as we discussed, there are some problems with that, right? So like if the point of a leader is to assemble a block, well then, presumably you got to give the leader a little bit of time to assemble their block. And the time that you give them is then a window by which anyone else can try to attack that leader. For example, by a denial of service attack, thereby forcing that leader to skip its turn. So I think everybody can agree that's a bad thing, but I also think it's a reasonable opinion that it's not bad enough to deal with all of the additional complications that come in from VRF sampling. And indeed, some of the major proof-of-stake blockchains do take exactly this approach, like Solana and Cosmos would be 2 examples. On the other hand, there are some major proof-of-stake blockchain protocols that actually do this VRF-based sampling, do actually really care about the secrecy property. Algorand being an example on the BFT-type consensus side, Cardano being an example on the longest chain consensus side. So those types of projects really have to do some additional work just so that the consensus protocols that they're using accommodate this quirk of VRF-based sampling, that it might produce 0 leaders, it might produce multiple leaders, right? Because if you think back to when we were talking about BFT type consensus, like Tendermint or longest chain consensus, right? There were rounds and there was always one unique leader for a round, right? That was by definition. We only considered all of those consensus protocols with 1 leader per round. So now if you're going to use VRF-based sampling, you have to go back and say, oh boy, what if there's actually like 7 legitimate leaders in a given round because of the quirks of VRF sampling? Like what is my consensus protocol then supposed to do? Now, the first of the 2 bad cases, right, so the case where actually you get no samples, right, nobody's VRF output is sufficiently small, intuitively that should feel like it's maybe not that big a deal, right, because all the consensus protocols we've been looking at, they already have to be robust to things like a Byzantine node being chosen as a leader and then just remaining silent, which is kind of the same thing as if there was no leader chosen at all. So obviously it's not good if nobody's chosen because it means it's like a time slot with guaranteed no progress, so that's going to sort of slow everything down. But you might not expect that bad case to interfere with like consistency or aliveness, and indeed it doesn't. So the tricky case is going to be that second bad case, where in a single round we get, let's call it sort of 7 legitimate leaders. So that's really going to require some modifications to the consensus protocol. And the modifications you want to make are going to be somewhat different for a BFT type consensus protocol versus a longest chain protocol. So we'll get into all those details, but not right now. So in part 3, those videos are going to be all about sort of the various issues that come up, extra details you have to handle when you try to couple proof-of-stake random sampling using one of the methods we're discussing here in part 2 with a consensus protocol like a Tendermint or a longest chain protocol. So that's what we're going to talk about, sort of details on the interface between those two, and that's the natural place to discuss how you modify a consensus protocol to deal with the multiple samples coming out of this VRF-based approach. The third option is the most ambitious one, which is to say, I don't want to make either of these 2 compromises. I want secrecy, and I want a guarantee that exactly 1 public key is going to be sampled. So that problem now has a name, which is Single Secret Leader Election, or SSLE. So this problem was first given a name and formally defined in a 2020 paper by Bonnet, Eskandarian, Hanslick, and Greco. There's also been some follow-up papers. I'll put citations in the lecture notes for this lecture. So at the state of the art at the moment, speaking in early 2023, we have in principle solutions to the SSLE problem. There are constructions that in principle give us what we want. None of those have been deployed, so the practicality of any of these approaches is still sort of an open question. So I would say this is on the very, very cutting edge of proof-of-stake blockchain design. And the next generation of blockchain protocols, proof-of-stake ones, coming out 2023, 24, 25, I wouldn't be surprised if we start seeing some practical implementations of those SSLE ideas. But speaking as of now, none of the deployed proof-of-stake blockchain protocols do use this approach. It's a little too experimental at this moment in time. So this is one of 2 points here in lecture number 12, where we're really going to bump up against literally the very cutting edge of what we currently understand, right? So single secret leader election and whether or not that can be done in a practical way, right? So that's sort of the first open question. And then the other sort of quite experimental tool we'll start discussing soon is verifiable delay functions, or VDFs. So that's something to look forward to. The final thing with respect to this VRF approach to proof-of-stake random sampling that I want to discuss is just a little more details on what does sufficiently small mean. So let's remember where sufficiently small comes up. So let's go to the previous slide. You want to be looking at the upper right part of the slide, and in particular that blue inequality. And remember, the whole approach to VRF-based sampling is that a public key is considered sampled if and only if that blue inequality is true. This, of course, is largely inspired by Nakamoto consensus and proof of work, where solutions to crypto puzzles are defined to be valid solutions if and only if they lead to a hash that's sufficiently close to 0, where there in Nakamoto consensus, sufficiently close is specified by a difficulty threshold that's adjusted by the difficulty adjustment component of the protocol. Here we're defining a public key as being sampled if and only if the corresponding VRF output, evaluated on the current randomness R sub t, if the VRF output is sufficiently close to 0. And so here again, sufficiently close is parameterized. We actually have 2 parameters, not just a threshold tau, but that also gets multiplied by some function of the amount of stake Q sub I that's been posted in escrow by the owner of the public key PK sub I. So you should have a solid feel for the left-hand side of that inequality. That's literally just the VRF evaluated with the person's private key on the current day's randomness, so we know what the left-hand side is. But what is the right-hand side? In particular, what is tau? And maybe even more, you might be wondering, what is this function f? All right, so let's just copy down that blue inequality here on this slide using our VRF notation. So the first thing to remember is that we really do need some function little f of the stake Q sub I on the right-hand side of this inequality, right? Because what are we trying to do? We're trying to sample public keys with probability proportional to the corresponding stake, probability proportional to Q sub I. And the left-hand side, if you look at it, the left-hand side of this inequality is completely independent of the amount of stake associated with the public key. Okay, it depends only on the public key and the corresponding private key, and it depends on today's randomness R sub t. But independent of what the corresponding Q sub I is, that left-hand side is always going to be the same thing. So if we want this inequality to be true more frequently with higher amounts of stake, so this public key gets sampled more frequently, the higher the stake is, well, then we need that right-hand side to be increasing in the stake Q sub I. The more stake they have, the higher the right-hand side, the more likely it is the left-hand side will be at most, or strictly less than, the right-hand side. All right, so we definitely need the function little f, but then the question is, what should little f be? And the answer to that's really going to be dictated by the Sybil resistance property that we want. We want someone to be unable to manipulate the probability with which it's sampled, no matter how it might spread its stake over multiple identities. So I said to first order, you should think about little f as just being the identity function, so that the right-hand side just scales linearly with Q sub I. That's approximately correct, especially for small stake values Q sub I, but it's not quite Sybil resistant. So in the rest of this video, we're going to derive, using Sybil resistance, what that function little f actually needs to be. So let's now fill in some of those details. I should say the rest of this video, it's a little bit, it's important, but it is a little bit specialized, a little bit technical. So I understand if you just sort of want to skip the rest of this video and proceed to the next topic of pseudo-randomness beacons. That said, my guess is a few of you are wondering about exactly how this sampling works. So I want to show you some of those details. Furthermore, we actually will be reusing this work in part 3 when we talk about how to stitch together proof-of-stake sampling with either a BFT type or a longest chain consensus protocol. So we will see it again a little bit later in lecture 12. The good news is that we'll be able to fill in these details in a quite systematic way using a two-step process. Step 1, we're going to think only about some public key that has associated with it the minimum amount of stake, so just one coin if you like. That's going to lead us to a method of choosing the parameter tau, and then the choice of the function little f is going to be forced by Sybil resistance. So let's start with step 1. So let's assume that all the stake amounts, all the q sub i's are integers, which would mean that the smallest possible stake amount would be qi equal to 1. That's basically assuming that sort of stake is denominated in the smallest possible unit of the native currency that you're using. So for example, the Bitcoin currency, there is some smallest possible fraction of a Bitcoin that's ever considered by the protocol, known as a Satoshi. So in this case, obviously, we only care about the value of little f at one point, evaluated at 1. And without loss of generality, we can just set f of 1 to be equal to 1. That's just a normalization. So in that case, the right-hand side of the blue inequality now just becomes tau, the difficulty threshold. The left-hand side, meanwhile, the VRF output, we're interpreting that as a uniformly random number between 0 and 1. So the probability that that's less than tau, well, that's just going to be equal to tau, right? If tau equals 1 over 100, then the probability that a uniformly random number from 0 to 1, which is how we're thinking of the left-hand side, 1% of the time it's going to be less than 1 over 100, 99% of the time it's going to be more than that. So in this case, there's only one thing to decide, which is the parameter tau, which is equivalently the probability that any given public key, which by assumption has the minimum possible stake amount 1, tau is the probability that any given public key winds up getting sampled. So we just have to figure out what we want tau to be. Now, the probability of selection is presumably going to depend on like how many public keys are registered in the contract, right? So if we have like 100 public keys in the contract, all with stake amount 1, well, then maybe tau should be something like 1 over 100. 1% chance that each person gets sampled. There's 100 of them, so that gives us an expected value of one public key being sampled. If there's 1,000 public keys in the contract, then presumably we want tau to be smaller, maybe something like 1 over 1,000, so that we again have in expectation one public key getting sampled. So as a first cut, tau equal to 1 over the total stake amount, targeting an expectation 1 sample. That's a natural place to start. As discussed in the past, maybe you want to fiddle with that a little bit, multiply it by 2, divide it by 2, etc., in order to trade off the frequency of the first bad case of having nobody sampled with the frequency of the second bad case of having more than one person sampled. So we figured out what we're doing in kind of a ridiculously simple case where for some reason every single public key in the staking contract has posted only the minimum possible amount of stake. What are we going to do in general for arbitrary q sub i's? So that brings us to the second step, which is really the clever bit. So for example, imagine that there's some public key that has 12 coins associated with it. So you think about the person that owns those 12 coins, and you say, you know, an option that person has available to them is to launch a Sybil attack, right? So they could generate 11 more public key, private key pairs, and they could register under 12 different public keys with 1 coin each, right? That's certainly an option. That's something they could do. So if we're going to be Sybil resistant, we need to make sure that we treat that person exactly the same, whether or not they register 1 public key with 12 coins, or whether they register 12 public keys with 1 coin each. But that, if you think about it, means we can actually reduce the general case of arbitrary q sub i's to the seemingly trivial case that we've already solved, where all the qi's are equal to 1. Right? Like imagine we're dealing with 3 public keys, right? So one that has 12 coins, another one that has 7 coins, and another one that has 13 coins. Well, we just said we need to treat the first person as if they're 12 Sybils with 1 coin each. We need to treat the second person as if they're 7 Sybils with 1 coin each. And the third one as if they're 13 Sybils with 1 coin each. If we do all of those things, we're really just working with a set of 32, in effect, public keys with 1 coin each. And we already know what we want the sampling probabilities to be from step 1. For example, maybe it's 1 over 32 for each of those 32 Sybils. So that's going to be the solution, right? So the detail we need to fill in is like, what do I mean when I say treat a public key with 12 coins as if it was 12 public keys with 1 coin each? What exactly does that mean? That's actually a pretty tricky question to answer, and there's multiple answers that make sense. So to see what I mean, put yourself in the shoes of a proud owner of 12 coins, who's going to register in the staking contract and is debating whether to do it under a single public key with its full stake with qi equal to 12, or alternatively whether to register with 12 identities, so 12 different public keys with 1 coin each. So in the first scenario, if you register under only 1 public key, obviously either that public key gets sampled or it doesn't. So presumably, you're kind of bummed if you don't get sampled, you don't get to do anything, and you're sort of happy if you do get sampled because, maybe you get to, for example, propose a block. In the second scenario, meanwhile, where you have 12 public keys with 1 coin each, it's really not a binary outcome, right? Now you have basically 12 different versions of the blue inequality, each in its own, presumably much less likely to be satisfied than before because the stake amount is 1 rather than 12, but there are 12 different blue inequalities. So totally possible that none of them hold, meaning none of the 12 Sybils wind up getting sampled. Totally possible that one of them holds, means exactly 1 Sybil gets sampled. Totally possible that more than one of the blue inequalities is true, in which case 2 or more of the 12 Sybils would be sampled. So a key question to understand in getting the details of step 2 right is whether or not it matters if 2 or more of the 12 Sybils get sampled. So in other words, if I'm contemplating a Sybil attack and spreading things over 12 different public keys, do I only care about at least one of those 12 Sybils getting sampled? Or do I more generally care exactly about how many? Like, do I get more and more value as more and more of my 12 Sybils get sampled? So the first version of step 2 that we're going to look at is going to assume that additional Sybils getting selected beyond the first one offer no additional value. Okay, so all someone cares about is whether at least one of their Sybils gets sampled. As we'll see, that is exactly the right version of step 2 to consider when we talk in part 3 about coupling proof of stake Sybil resistance with longest chain consensus. So that, if you think about it, actually uniquely pins down the function little f. So for example, if you want to figure out what f of 12 is, well, that should be set so that the probability of sampling a public key with 12 coins is exactly the same as the probability of selecting at least 1 out of 12 Sybils, all with exactly 1 coin. So that's how this 2-step approach toward choosing the sampling thresholds works. Okay, so first you just figure out what you want tau to be. Tau, again, the probability that you'd sample a public key with the minimum possible stake amount, a stake amount of 1. Again, that's generally a function of the total stake, maybe something like 1 over capital Q, where capital Q is the total stake. And then you can generalize to all QIs, just if you have some arbitrary stake amount Q sub I. I'm just conceptually going to flip Q sub I different independent coin flips, each coming up heads with probability tau. That's like trying to sample each of your would-be Q sub I Sybils. And then I'll sample you with probability that's exactly the same, just by definition. I'll define the sampling probability as the probability of one of those Q sub I biased tau coins coming up heads. And so what's cool is you can see, without doing any computations, without any formulas, why this approach must give you Sybil-resistant random sampling, why sort of a node cannot affect its sampling probability, why it does not matter how it spreads its stake over various accounts. Because at the end of the day, however many accounts it uses and whatever the balance of each of those accounts, ultimately its QI total coins are going to be treated as QI Sybils in total. So it literally just doesn't matter how you split across accounts. Your sampling probability at the end of the day is going to be the same no matter what. So very cool how much understanding we can have of this approach and why it's Sybil resistant without writing down any formulas. Of course, if you were going to code this up, you actually would need those formulas. You need to know exactly what is the formula for the right-hand side of the blue inequality. And it turns out there's actually a very slick implementation of that. So let me just write that down here. So specifically, this idea is equivalent to setting the right-hand side of the blue inequality to the expression 1 minus e. Here e is the base of the natural logarithm, 2.718 dot dot dot. 1 minus e raised to the minus stake amount q sub I times a parameter mu. Mu here, that's just a reparameterization of tau. Specifically, mu is the natural log of quantity 1 over 1 minus tau. All right, so let me just talk through this slick implementation a little bit to relate this to things we've said in the past. So first of all, remember what tau is, right? So tau is the probability that you're going to be sampling a public key with the minimum possible stake amount, like a stake amount of 1. So tau is generally going to be a number that's quite close, just barely bigger than 0, right? Like if your total stake amount is 10,000, you might expect tau to be something like 1 over 10,000. Now let's look at mu, which is this sort of function of tau. Well, because tau is so close to 0, right, that means 1 minus tau is going to be barely less than 1. 1 over 1 minus tau will be barely bigger than 1. You take the log of that, you get something that's barely bigger than 0. So mu will itself be barely bigger than 0, and in fact, it'll be very close to tau when tau is small. So not a big difference between mu and tau. So moving on to the right-hand side of the blue inequality, right, that has the form 1 minus e to the minus x, where here x is going to be the parameter mu, which again is basically the same as the parameter tau, times scaled linearly by the stake amount q sub I. And one way to understand this, the right-hand side of this blue inequality, is to remember that e to the minus x is very close to 1 minus x when x is close to 0. Okay, 1 minus x, e to the minus x, if you just plot those two functions, right around x, you'll see that they're very close to each other. And so that means e to the minus qi times mu, that's roughly the same as 1 minus qi times mu, when qi times mu is small, which actually means this right-hand side is basically qi times mu, which is then basically qi times tau. So you might remember back when I first introduced this function little f, I said don't worry about it for now, just think of it as the identity function. And now you can see why I told you to think of it as the identity function, which is as long as tau times the stake amount q sub I is small, then in fact the right-hand side is quite well approximated by just tau times the stake amount. So that would be like having the function little f equal to the identity function. I think it's also instructive to just see this formula in action a little bit to connect it to Sybil resistance. So as a thought experiment, let's think about someone who owns Q coins, like say 12 coins, and is contemplating representing itself with 2 public keys with stake amounts Q1 and Q2, which sum to Q. So like 5 coins in one, 7 coins in the other. So if this person actually does put all 12 coins into a single account, well then either it's sampled or it's not, and the probability with which it's sampled is just equal to the right-hand side of this blue inequality. So 1 minus e to the minus q times mu, like 12 times mu. On the other hand, suppose the person uses 2 public keys, like 7 coins in one and 5 coins in the other. And remember our assumption that this person only cares about whether or not at least one of their Sybils is sampled. It gets no additional benefit if both of its Sybils get sampled. So let's think through that probability in the second scenario, right? The probability that at least one of the 2 Sybils, either the one with 7 coins or the ones with 5 coins, that at least one of those gets sampled is 1 minus the complementary probability. The complementary probability being the probability that neither of the 2 Sybils gets sampled. So this expression is going to be 1 minus something, where for us, something is the probability that neither of the 2 Sybils, neither the one with 7 coins nor the one with 5 coins, gets sampled. Those 2 events are independent, so we can look at the product of their probabilities. Okay, so the probability that the first public key does not get sampled times the probability that the second key does not get sampled. So think about the first one. Okay, what's the probability that the Sybil with 7 coins, say, doesn't get sampled? Again, 1 minus the complementary probability. 1 minus the probability that it is sampled. We know what that is. That's just the right-hand side of the blue inequality. That's just going to be 1 minus e to the minus q1 times mu, or in our running example, e to the minus 7 mu. So for the first Sybil, probability of sampling, 1 minus e to the minus qi times mu. The complementary probability, the probability of not being sampled, is just 1 minus that, which is then just going to be e to the minus q1 times mu. And of course, same thing for the second Sybil. Probability that it is sampled, 1 minus e to the minus q2 times mu. The probability that it's not sampled, just e to the minus q2 times mu. So the probability that neither is sampled is just the product of those two probabilities. Again, e to the minus q1 times u times e to the minus q2 times mu. Okay, so of course those two exponents on the right-hand side add, and so because q1 plus q2 is equal to q, actually these two expressions are exactly the same thing. So this formula confirms the Sybil resistance property we were expecting. That it really doesn't matter if you split your stake or not. The probability that at least one public key under your control gets sampled is going to be the same no matter what you do. We, of course, were expecting that given the conceptual discussion, given the strategy of just always treating someone with 12 coins, say, as if they were 12 Sybils with 1 coin each. So that's the right way to define sufficiently small in scenarios where there's no benefit to anybody from having more than one of its Sybils selected, which, again, as we'll see in part 3, when you couple proof-of-stake Sybil resistance with longest chain consensus, this is generally the version you want to use. As we'll also see in part 3 of this video, if you couple proof-of-stake with BFT-type protocols, you usually want something different. Conceptually similar, but the details are going to be different, specifically in step 2. Now let's think about the case where, if someone's doing a Sybil attack, for example, using 12 Sybils with 1 coin each, let's assume that it actually matters to them exactly how many of those 12 Sybils get sampled, as opposed to previously when we were just thinking about the binary predicate of whether or not at least one of the 12 gets sampled. So we, again, want to be guided by an equivalence we're looking for between two scenarios. Right? Scenario 1, where someone stakes, say, 12 coins under a public key. Scenario 2, where they stake 1 coin each and 12 different IDs. But now let's think about the case where in that second scenario with the 12 Sybils, the person actually cares about exactly how many Sybils get selected. It cares not merely about whether at least one gets selected, but it really prefers 2 to 1, it prefers 3 to 2, etc. Well, if we want it to be treated the same in these two scenarios, now there's 13 different outcomes that could happen in the second scenario. Anywhere from 0 to 12 of its Sybils could be selected. So I guess that means we need to modify what we're doing in scenario 1 so that there's also 13 different outcomes. So if we have someone staking 12 coins, it is no longer going to be as simple as just we either sample them or not. We're actually going to be sampling their public key with multiplicity. Okay, so we will sample them some number of times between 0 and 12. Now that, of course, means we need to specify a probability distribution that these multiplicities are drawn from, right? So if someone stakes 12 coins, what's the probability that they're chosen 0 times? What's the probability they're chosen 1 time, 2 times, etc.? But again, we can just be guided by the fact we want them to be treated identically to as if they had 12 different identities with 1 coin each. Because in that case, that corresponds to step 1. We know what's going on. Each of those 12 identities, it's like an independent coin flip that comes up heads with probability tau. Remember, that's the definition of the parameter tau. So we just should say the multiplicity should be sampled from the exact same distribution you would get were there 12 Sybils with 1 coin each. And actually, that's a famous distribution, right? That's just the number of heads that come up when you flip Q coins each with bias tau, something known as a binomial random variable. Okay, so bin of Q comma tau, that's literally just the number of heads you get when you flip Q independent random coins, each of which comes up heads with probability tau. So Sybil resistance, I hope, is kind of obvious, like without any formulas, just from this conceptual discussion. Right? It doesn't matter whether you stake 12 coins in one public key or whether you use 2 public keys to stake 7 and 5. Either way, that's all going to wind up, it's going to translate to 12 independent random coin flips on your behalf, and you will just be credited with the total number of those coins that come up with heads. It doesn't matter if all 12 coins are flipped in a batch, or if 7 are flipped in one batch, 5 in a different batch, and the results added. Either way, it's going to be exactly the same thing. A little more formally, we're using the fact that when Q equals Q1 plus Q2, the binomial distribution for Q coin flips with a bias tau, that's exactly the same as the sum of two random variables with Q1 and Q2 coin flips respectively, and that same bias tau. So in the first version of defining sufficiently small, right, we had sort of the conceptual discussion from which Sybil resistance was conceptually clear. Then I gave you kind of the slick implementation, which would be relatively straightforward to implement. So here for the variance, where you're sampling with multiplicities, we've talked through the conceptual approach, and again, why it should be sort of obvious that Sybil resistance is going to hold. Once again, there is a more slick implementation where you really just sort of evaluate a VRF and then look at sort of which interval it lies in to figure out what the multiplicity should be. I'll leave the details of that slick implementation as an exercise to the reader. So that finally wraps up everything I wanted to tell you about VRF-based random sampling. And this really brings us quite close to the state of the art, the sort of the cutting edge of how modern proof-of-stake blockchain protocols are designed and implemented. There's still one obviously quite unsatisfying thing about the discussion so far. We're still to this point assuming that R sub t is sort of perfect randomness that falls from the sky. We're assuming access to an ideal randomness beacon, which probably doesn't even exist. So there's still the question, in a concrete implementation, how are you going to define that randomness or pseudo-randomness R sub t at each time step? And that is exactly the issue we're going to start addressing in the next video. I'll see you there.